and what are the future scope. Mainly, we'll see that. So this discussion will broadly cover that what is the on-chip antenna. Mainly, I will focus on the introduction why on-chip antenna is required currently and why we should maybe if we are choosing any new topic on the antenna, why we can choose that. After that, what are the design challenges involved in the on-chip antennas? What are few methodologies and techniques which we required when we are designing those on-chip antenna, and then some successful design models which we have designed during our research, and future direction and emerging trend. So we will see. So first, as we know that semiconductor industries and specifically that IC manufacturing follows that Moore's law, right? Moore's law, everyone knows that every year the components are going to be decreased in like half almost, you can say. So because of that, the compactness in the IC system means more and more over the year it is getting compact. Right, you can see earlier it was through that development earlier some MCM type of systems we are getting, which is multiple chip module, where in a single chip or single maybe you can say there's substrate, there are multiple chips we are placing. Like if you have seen some old television sets, the PCB, there are multiple ICs was there kept in place there in that same system, right? So after that, the development happened, and then they gone for that system in package type of. So because that area, the chips are there, but it is kept on a single substrate, and that is very wide. So what they have done, they have this researchers done that they have start putting those ICs. Maybe you can see in that stack up manner, so that it takes the lesser space, right? So it was. Maybe that is called system in package, right? So then we after that we went for system on chip. What is the first one? It is written that the top, that is on chip system, right? All those ICs, like all that, like a system is containing like different types of components. Digital ICs are there, RFICs are there, optical ICs. So all those ICs fabricate monothelically in a single wafer, right? And then a complete system, you can say, on a single chip as we were getting. But what there were some challenges also there, like when we are designing a MCM module. So suppose one RFIC is damaged, then what we can do, we can remove that RFIC and put that into the system, and our system will be working. But in SOC case, that is not the thing. Like all those ICs are kept in a single package, right? Single chip, single wafer. So what will happen here? If a single component, suppose RFIC or digital IC or any optical IC is damaged, now the complete system gone. So that was actually the latest technology SOC, but uh, because that is creating very much financial loss also when we are going for that manufacturing. Because of this issue, they have shifted to this a compromise between SIP and SOC, which is in between that SOP, which is multiple ICs. Some ICs can be stackable also, some can be in a, like you can see in the picture here, it can be, let me use a pointer here, this way. So some can be put it in the horizontal manner. So overall system, a compact system we are getting in terms of SOP. Now, why that compactness is required, right? Now you can see because of this compactness, because of that VLSI technology is growing on every day, that different nodes. Earlier, some year ago it was 180 nanometer, then 130 nanometer. Nowadays even 20 nano and 5 nano is also there. So now you can see the device is compacting so much. These RFICs, what is the problem with RFIC? It is having analog components. Like I can show you here. If you see here, inside that RFIC, just now what we have seen, there are different components like RF front end, everyone knows. So there are mixer, power amplifier, uh, voltage control oscillator, all those things in the RF front end system. Now, if you see here, in this RFIC, if a single front end, if you see, the antenna should also be there, right? This IC is here, but antenna is kept here outside of the PCB, or you can say outside of the IC, right? So this is a system in package type of thing where some components which cannot be kept in the IC, they can kept in the outside of the IC, and other components, other IC components, we can stack up and make it compact. This is a compromise what I have just discussed about. Now here, that antenna being the largest component, because when we are designing the antenna, uh, and suppose it is designed for the lower microwave frequencies, it will be not compatible with the chip size. So that's why it is kept outside. And being the analog component, very hard to miniaturize it, or just like the other components of what we are using that in VLSI. So that on-chip antenna emerges as a solution for this problem. What on-chip antenna do? This antenna which is designed on the PCB, now we will put that antenna also inside that RFIC. So that's why the topic name, what the title of the discussion was, next generation RFIC. So actually, this antenna is now kept inside this RFIC. You can see here, this RFIC earlier was having mixture, power amplifier, VCO, but through these connectors, that antenna was put, which was already outside of the PCB. Now it is also come inside the single chip. So this becomes system on chip of type of device, right? Now what will happen with this? You can see here the connectors are there, right? These are the connectors which is connected from IC to the antenna. Now these connector need specific uh, impedance matching also, right? The connectors are anyway, it is having the losses. Now, so you have to match those impedance, but here directly you can use that same impedance of that whatever the LNE, with that directly you can connect to the antenna. So that generally the connectors are having fixed impedance, right? Fixed, maybe you can say that generally nowadays whatever available 50 ohm, 60, 75 ohm. Now here any impedance that connectors impedance matching is not required. Directly you can match with the directly with LNA. So that impedance matching is requirement is eliminated, right? At least you can say 50 ohm impedance matching. Impedance need to be matched, but it is not required now 50 ohm need to be matched. Okay. Second thing, now the system, what we are saying that futuristic RFIC, or you can say the next generation RFIC, now the complete RFIC is truly wireless now, right? IC is truly wireless because earlier to make it wireless, we have to connect it to an antenna. Antenna was outside, but now this IC, what is designed on a complete chip, is now truly wireless. So that is what we are saying that, okay, now this on-chip antenna is going to help you to generate or give or develop a futuristic next generation RFIC, right? But if that is simple, or maybe if before that, how to do that, why we should go for that on-chip antenna. Because many people, at least in my students, are generally asking, sir, why there are many types of antennas are there? Why we are doing these on-chip antenna research to give them the motivation, because the Indians are not, without checking everything perfectly, they are not moving toward that side. So to give them the motivation, I'll explain them in terms of the Indian semiconductor ecosystem perspective. So one of all of you know, right? This India is investing many 76,000 crores in this India semiconductor mission, right? In that now we are developing our own ICs, right? We are now making India Atmanirbhar actually by making the reducing the import, which we are heavily dependent in the near past. that to importing those ICs from the outside countries, right? Now, if we are able to make our own chip, even we can export in future, and that will also uh, innovate in terms of research also and jobs also, right? So in that perspective, this on-chip antennas are very critical, right? Because other things, what we are discussing, if you are seeing that LNA, VC, all those things are already developed, already put kept inside the IC. So what is the next? How you can go one step further? Because now, if India start doing the same thing what is already done or already developed, then there is no use of this mission, right? We need to think futuristic. What is there going to be in the future? We have to predict and work for that. And this time we'll try to make it faster than what the other country has already done earlier. So, and they are also doing. They are also. So this is not that much irrelevant, right? Now, currently, in current scenario where India is moving toward the semiconductor is developing that mission, this on-chip antenna understanding and the research, if you are going to pursue, this is going to be very critical in your research. Right. Now, how this on-chip antenna, you can see here, these connectors, what we are using here, just like I've shown in the previous picture also, this will be removed totally and it will make it complete RFIC, truly system on chip and truly wireless system we were able to develop, right? And that will be also low cost, mass production we can develop. Another motivation, what I generally give to my students, that is ISRO. When we people are hearing that ISRO word, it is coming in our mind that what we can do for our ISRO, because we have heard many success stories, and when we are comparing it with the other outside of us, uh, like NASA is spending so much money, and that India is doing in such a small amount the same thing. Like many other, not only NASA, many other uh, space research organizations are there, right? So when we how that ISRO is working, what are the current work what ISRO is working on? So one of the current work ISRO is developing that navigation IC, or you can say navigation of Indian constellation. It is a replacement of uh, our that GPS what we are using. Actually, that service is also we are taking from the outside, right? So now India is developing its independent satellite navigation system, which is Navic, right? All of maybe some of you have heard that. In that also, that Navic chip is going to be developed. And the current architecture, you can see the antenna is externally kept. So if we can, and for that information, those who are working in Hyderabad or in the Andhra Pradesh or Telangana, that I think Navic chip development is happening in Hyderabad itself. One is, I think, firm is there which is called Manjira. So if you want, you can search in that regarding it. So they are developing, and they are. If you can go and visit there, so maybe you can see that how that thing is working. So here we can see that antenna is again kept outside, and to make this, that GPS people are already working on that. Now to make this futuristic Navic receiver on chip, we can develop this on chip antenna also, and because with this help of the on chip antenna, we can make this a compact lightweight chip, that Navic receiver chip. Why I am saying receiver, I'll tell you. But that we can use, and that applications you can see whatever the GPS application, it will be replaced by this. So either it in smartphone or drones or wearables or defense, everywhere that GPS is required. So there we can replace, and it will be make this India our mission, independent, Atmanirbhar, all those things. It will be uh, following, right? So that is the main motivation to work on those on-chip antennas, because many antennas are there. Like the questions are very much correct, right? Why we should work? So there should be a motivation. So these two motivations are enough to work on this on-chip antenna. Now, some students are asking us, sir, if it is okay, that is the thing. If that antenna development is required, we have done many antennas, many patch antennas, and BTech also. So why that on-chip antennas is still not on the mainstream? If that on-chip antennas are that much useful, why these are not still on the mainstream? Why we are not uh, why we are not using those on-chip antenna? We are not developing and we are not using on any RFIC. Why? So the answer lies in the design challenges. So now
Hello,
we are
sir.
moving toward the design challenges. Yes, yes, sir.
Sir, sorry for the interruption. Voice is a little bit slow, sir. Please, participants of the line.
Oh, okay, sir.
Yes, sir.
Right.
Yeah.
Okay, so now we are now moving toward the design challenges of the antenna, like on-chip antenna. Now, so as I told that uh, it is there that okay, that motivation is there. Now how to design that, and what if we are designing that, what are the design challenges? The first design challenge, it's size. Now if you are working, if you are designing these antenna for the current system, which where most of the 90% of the system are working on the lower microwave frequencies. Now, what the problem will there? What will be there? If you are converting those antenna, generally, if I take normal antenna, that will be lambda by 2 size, half wave or quarter wave antenna. That lambda for the lower microwave frequency is such big, so that if you are designing that antenna, on-chip antenna with that size, it will not allow it to accommodate inside the chip. So in that case, you need that miniaturization of that antenna. You need to make that antenna compact. Even it is working for that frequency, you have to make it compact by reducing its aperture. Now, as you are starting at doing the aperture reduction, what will happen? The antenna's gain and radiation performance will drastically reduce. So if you are start making it to reduce the size of antenna, then these problems will be there. Now, but as we are making the on-chip antenna, that is compulsory. You have to make the antenna size. So that is the challenge, that how you are maintaining that radiation performance from the antenna as well as its size reduction. When you are reducing the size, as I told, the poor radiation performance will be there. That is not only due to the size of the antenna, but because of its substrate limitation. Mostly the ICs firm, what they are firm is uh, that fabricating their ICs, they are using silicon substrate because of this abundant availability and low cost. Right now, silicon substrate is very much suitable for the other ICs component. Any ICs that silicon is very much favorable. That TPC, that temperature coefficient, everything is well suitable for the IC manufacturing or other component, whatever the IC component. But when it comes to the antenna, the problem with silicon is it is having very low resistivity and very high dielectric constant. Now, when the dielectric constant will be high, what will happen? Substrate dielectric constant high and with low resistivity, both are harmful for the antenna design. You can see this picture here. The most of the EM radiation will be absorbed by the silicon itself, right? The substrate itself. So the radiation what we are looking for from the antenna, right, that will not as good as we want, right? It is not in the air, but it will be absorbed by the substrate itself. So that is the prime challenge, that how we can uh, increase this radiation from here to here at the top in the air, right? So that is the first challenge. or maybe second, you can say. The other than that, now the major challenge what uh, people are uh, doing the research on, they are developing one of the design rule check. Like when we are designing IC, any firm if you'll go, there are a design rule check. Okay, if you are designing this component, these are the steps, and this is the thickness of the substrate, this is the oxide thickness, this is the metal percentage, or that how much percentage of part of the metal you can use at this layer. There are multiple layer, right? You can see here this white lines are here. You can see these are the metal layers sandwiched in this silicon substrate, silicon dioxide. So in these metal only we will able to design that antenna. Generally we are designing this on-chip antenna, the top metal. Other metal layers we are using for the other circuit components of that IC. Now in that metal, what will happen for other components of the IC? There is a rule, but there is no specific rule yet set for the on-chip antenna design. So what we have to do, we have to follow those IC's component rule. What is any specific suppose component LNA we are designing. So what rule we are following for the LNA design, we are using that till date for designing the on-chip antenna, which is sometime not suitable for the antenna manufacturer. Other than that, one of the most challenging aspect is crosstalk. When that is another research area which currently I'm exploring also. That is crosstalk issue. How we can reduce this crosstalk. Now you can see if there is an on-chip antenna design, any other component, even if it is distance is 6 mm or 5 mm or 10 mm, this is also going to impact the working of this component, right? Because the radiation, whatever is going to be emit from this on-chip antenna inside the IC, that radiation can impact the performance of the other component inside the IC. So how we can reduce this, any specific method or any techniques which we can use and reduce this crosstalk. That is picture is taken from my recent work. It is given here at the bottom. If anyone interested, they can follow how to reduce. One technique is given there. That defected ground technique can be used to reduce this crosstalk between two components. So these are the prime challenges associated with the design of on-chip antenna. Now, so challenges is done. Now, if these are the challenges, how we can overcome this? So for this, we have gone for the what over the research is reported till now, till date, right? And this report is also published in one of the work that we have published in 2023, that is current trend and future perspective. From that, if you'll see, there are multiple techniques have been told and been reported which can reduce that radiation in the substrate. Like one of the technique is dielectric resonator, many of you are familiar with. What is this dielectric resonator will do? It will be either designed along with the on-chip antenna at the top of the metal, right, or that where the on-chip antenna is designed. So if the resonator is having more dielectric constant than the silicon, then what will happen? The more EM energy it will be absorbed or moved toward the air or resonator instead of that uh, substrate, right? So you can see here, generally in the on-chip antenna, this gain what we are seeing here is 1, 7, 10 dBi. That is not the common gain. In on-chip antenna, most common gain generally minus 20 dBi, minus 30 dBi. Even some of the gain is reported minus 60, minus 50 dBi also. That is also accepted because that is the thing, right? If you are not uh, utilizing any technique to improve that gain, generally if you normally design a common antenna, that that is a case, the gain will automatically reduce because you have reduced the size of the aperture as well as you are designing on the silicon. So there are no compromise. You have to make some compromise. Either you can keep the design same for the lambda by 2, then only it will be increase, or you can, instead of using silicon, you use some other substrate. So these are the things, right? So when you use the DRA, you can see the gain is now shifted toward the positive, right? I told you minus 20, minus 50, and minus 60 also reported. Now the gain is positive. Even when we are getting 0 dBi gain also, then we are very happy that, okay, now our antenna, we have done something. So that is the thing. And because of that only, when I told you, I will tell why I told that receiver in that receiver antenna. That because of this less gain, the on-chip antenna is having very less, means what you can say, the area, working area. Like it can be only used for the maybe micrometer or millimeter range, or maximum to the meter, 1 or 1 meter maximum. That is the range where we can use a on-chip antenna. So it can receive well, but when it start coming to the transmission side, transmitting, it will radiate very for the very less distance, right? The coverage area is very less because of this, because it is having very less gain and efficiency, and also the application where we are using this antenna, it is used inside the chip, so we cannot put more power to radiate it, right? The chip is generally working in microwatts, few microwatts to 100 microwatts maximum, right? So that power we are not able to provide as an input. So these are the things that only mostly its applications are as a receiver antenna. Now, so these are the one technique, DRA. Another technique for this AMC is also reported, artificial magnetic conductors, where we can use any of the other metal layer what we have seen in the CMOS structure. Any of the metal layer we can use to improve the gain of the antenna by reflecting at particular resonative frequency, that AMC work as a reflector, and it start uh, reflecting instead of going toward the EM wave, instead of going toward the silicon substrate, it start going toward the. So that is another technique which has been mentioned. One of the another technique is micro machining. This was actually different from the techniques what we have seen those two techniques before, because this is post processing technique. Once the on-chip antenna is completely designed, what micro machining technique does, it removes that silicon substrate from the bottom of the antenna. Right, we'll see. We have worked on that also. We will show when we will see that some models. So what we'll do, we'll remove that extra part which is unnecessary, unwanted there in the wafer over the below the antenna. So what will happen, instead of getting epsilon or 11.9, for which is exactly for silicon, now it is epsilon effective with air and silicon. Okay, so it is anyhow it is going to be less compared to the only silicon. So that is also helps to enhance the gain or the radiation performance of the antenna. You can see here some positive gains are reported. The technique MEMS will also MEMS what it will do, instead of fully implemented on the substrate, some part of its using MEMS technology, it is suspended. It is not touching to the substrate. So that part is having less loss, and it helps to increase the radiation performance of the antenna. So these are few techniques which was reported, and based on these, we have also done some design, but I'll not show you those designs directly. I'll try to go step by step so that you people, those who want to really go for and choose a topic and as a one-chip antenna for the research, they can see that how we can go, from where we should start. So the first, what we'll do, the target is we can go for the compact antenna as well as the efficient on-chip antenna. Efficient means radiation efficient. So for that, what we'll do, we know that how to design a simple patch antenna. So we know that patch antenna, how it radiates. Same patch antenna, what we'll do, we'll design on the silicon substrate. We'll not do anything else, and then compare the results. That how actually that silicon, then you will see that okay, that is what the silicon's impact is there in the on-chip antenna. Like when we are designing that patch antenna, same patch antenna in FR4, and when we are designing that antenna in uh, silicon, what is the changes are there? That is how we should start, because with those antennas, everything calculation, how to do that width and length calculation, how that inset calculation, all those things we know, right? So we no need to do extra, only to see the impact of the on the radiation of this silicon. We'll do that. So that is the first step. What I'll suggest if you are going to start the design on chip antenna. Then we have in this we have introduced some asymmetry, and that is allowed us to get a circular polarized on chip antenna. But that was not the target. The target was to see how that on chip antenna is going to behave when we are designing it on a simple silicon. Here we have not used any between any metal layer, also just simple top layer, and design that on chip antenna on a substrate. So we see here that the gain we directly what we have got is minus 10 dB, minus 5 dB. Now, why it is minus 10, minus 5? Because we have not reduced the substrate, the antenna size that much, right? It is 30 mm cross 25 mm. So as I told, that patch size for 2.45, generally that is the calculation. So we have not reduced the size. Still we are getting that minus 10. If you design a normal patch on the of that size on a for 4, you will minimum you will get 6 or 5 to 6 dB again. But here you can see here directly minus 10, minus 5. After that asymmetry is there, that it will little bit increase, and that is also directive gain. So that is how we can start designing that on-chip antenna. And you can see the gain here, it is almost minus 9.2 dBi was the final gain. And that is a result of circular polarization that I am not going now. Okay, so that is the first. Then we can do that analysis for the other antenna, other type of antenna like say, fractal antenna, slot antenna, many types of antenna we know what we are designing. So that is also another antenna we have gone through. And we found that, okay, that gain is anyway, it is coming less, minus 20 dB, minus 19 dB. And these works are published, right? It is not like well accepted in good journals also, because they know also, right, that the chip antenna getting this much gain also is very well achieved result. So these results are also published. Maybe you can see here some journals and the conference paper. And that fabrication here is, if you'll ask that, sir, where we are going to fabricate these antennas. So that thing is also at that time when I was working, and maybe you have heard in introduction also, we have done some collaboration with IIT Bombay, ISC, Bangalore, and SCL Chandigarh. It is because of that only, because in India at that time only 2-3 labs was there who were fabricating this, working on this semiconductor fabrication. But as now India is developing their lab, it is that on-chip antenna topic I will suggest you please now you can start working on, right? As a new researcher, you can choose that topic, and that fabrication facility is now that is better compared to the last means 10 years ago what was there. So another thing, what after that, now coming to that other reported design, what we have done to improve, now we have seen that, okay, that gain was reducing when we are designing. To improve that gain, what we have done is start putting the extra layer there. So you can see here, this was the earlier where the silicon, that aluminum was kept on the silicon substrate and SiO2 layer. Now what we have done, we have start putting some thin film layer. This is a ferrite film which is kept in between the antenna and the SiO2 layer. This ferrite is having very high resistivity, right? So other like unlike that silicon and SiO2, and also that is not allowing that EM wave which is coming inside the silicon substrate. So the result you can see here, it is quite high gain improvement you can see here. But earlier it was minus 45, now it is minus 30, 15 dB almost gain enhancement we have got after putting that film. So another thin film again we have kept here. It's in between the aluminum and SiO2. You can see that is hafnium dioxide. Again, this is a film which is having very high uh, resistivity. Okay, so it again helps us to improve the gain. So this is the way one by one we can go, and we can see time change in the results how we are getting it. And these all are reported work. If you want, you can follow these uh, paper, right? And so this is how we can. After that thin film, what we have done, we have tried to use that other metal layer what was there in between. We have seen the only we are using one metal layer till now, but as the metal layers are available, so either you can use as AMC or simple reflector like what we have used here. We have used this bottom metal layer as a reflector or partially shield layer also you can say. It is shielding the EM wave from toward going toward the silicon substrate. So again, that is also going to help to reduce the that losses in the substrate. Okay, and help to enhance the gain also. Now you can see here we have slowly going toward the antenna miniaturization also. So for simple patch, now what we have done, we have used the meandering technique to reduce the antenna size, electrical length, right? So increasing the electrical length here, but reducing the size using that meander technique. So meandered loop technique here used to uh, uh, is what you can say, reduce the size of the antenna, physical size, but it is not reducing the electrical size of the antenna. Okay, so this bottom metal layer helps us to enhance the gain also of the antenna. It is something like AMC, what maybe we have seen. Okay, and so these are some results, right? And successful reported designs, what we have done. And this work at that time we have fabricated and measured everything in SCL Chandigarh Semiconductor Lab, and we have got very good result. I mean, so getting that the same frequency what we have designed is also challenging their measurement also. But thankfully they have at that time uh, because starting a work which is not suitable because FR4 and other antenna we can fabricate anywhere in India, in every city almost it is there. But doing that and for that collaboration is become very helpful to complete that these works. Okay, so maybe if required, nowadays still we are in collaboration, so we can help you to get that. So these are the some results, right? We can use, and one of the things we cannot use simple microstrip antenna like feed here. You can see here that is another difference when we are designed from the normal antenna to the simple on-chip antenna. Here we are going to use CPW feed. Why CPW feed? Because it allows us to keep that ground because on-chip antenna is not having at the bottom of the silicon nowhere you have seen right till now in the structure that is there any ground metal is there because ground in on chip it is not possible to keep any ground. There is no ground plane here below the silicon wafer. So to keep that ground here, this you can see here every antenna what I have designed, I have used this ground pads here, right? Here you can see the ground pad is there. So at the top, and this can be only fed using CPW line, not that microstrip. And as a thickness also very less, it is very thin that wafer. We cannot use simple RF connector to. So the GSG probe, specific probes are there which will be used to during that measurement. And in the same way, to make it more practical, you have to also use CPW feed instead of normal microST feed when you are designing the on-chip antenna. So, okay, with all these results, I'm not going to show many other results. We have gone for the DRO also, that micro machining also. All these things we have gone and published. So if you want to follow that, you can follow the HCLs. Because the time is less, I'll just directly jump to the future scope of that. What where you can work if you are going to. So nowadays, maybe you have seen if some application specific ICs are designed, so they are not hesitating to use a better substrate also. So we can use some emerging substrate like gallium antimony compound, indium antimony compound, gallium nitrate. All these substrates are also nowadays used in a application specific, where the cost, where the that losses matter, right? There we are not mm, generally using that silicon because of fussy nature. So they are using that very high resistivity and good quality of substrate, better than the silicon. So that also can be used in the on-chip antenna design in future. Other things like space applications, we can see there in space-based design, there are very requirement of the compact systems and design. So we can also use those complex uh, uh, system, right? We can also use those with on-chip antenna to design those complex system, right? Similarly, this 5G and 6G, and in future maybe you will be seeing 7G also. They are uh, demanding those compact devices. So there also you will get definitely these applications of the on-chip antenna. Moreover, the terahertz devices, because that in terahertz devices it will be useful, and it is useful because at that terahertz frequency the wavelength will be very small. So even if you are designing that lambda by 2 antenna, that will perfectly fit inside the chip. So in terahertz applications are, because in India, why we are not using that? Some issue is there with the facilities, like measurement facility restrictions are there. There's components of the devices what generally normal institutes are having. They're not suitable for the measurement and the characterization of the terahertz devices. So we are limiting ourselves to the microwave and some mm waves. But still, that nowadays the labs are developing and that people are using. Some institutes are still, maybe they have installed those and equipped with those components which may be helpful to characterize those terahertz devices. There also you can, like, that is a very good area where that on-chip antenna can be used. Okay, so these are some future is area where if you want, you can work. But with this, I'll sum up my session. If any query is there, please. Okay, I can see some questions already there. So Ravi Kumar sir has asked that what
Sir?
actually the negative gain represents. Yes, sir. Yes, sir.
Sir, good evening, sir. Sir,
Good evening.
being from the antenna field, which one is better, sir? Whether to focus RFIC?
So if you are working in an RFIC, you should, what I'll suggest, you should work in a form of group, like some person which is specific in the amplifier design, who has knowledge that amplifier design, then you can collaborate and make a complete system. As a single individual, it is very hard to work on that RFIC completely. That LNA itself is a, maybe many type of LNAs nowadays design researches are going on. Amplifier, power amplifier, maybe you have seen that they are designing compact power amplifier with having the same performance what the bigger one have. So that, so I suggest if you are working individually, go for a single component of any of the RFIC component, either LNA or power amplifier or on-chip antenna. Second, I hope I have answered. And that's for simulation
Yes.
tools, you have to practice. You have to practice, right? When you are starting and keep doing, keep learning. In that way, maybe you can, like if you are using ANSYS tool or something, that ANSYS mm, are providing their time to time their courses. So you can keep searching for those courses, and generally 15 days and 20 days they will ask you to come and uh, attend their course. The experts from the NCS itself, they will guide you. And not only NCS, others like what are the tools like CST and FECO also they are giving the training. So that thing you can understand.
Is there any
Can I
specific
take
courses,
these?
sir?
Specific courses. You can search in the ANSYS website. There are courses. And any tools specific course is not there. You can maybe just discuss with those person in the ANSYS. They will be guiding you how to. When I have started working on the HFSS, I have gone for the course in the Bangalore ANSYS software means that where this company is located. So they have given that 15 days course. After that, there is everything in the website also, some tutorials and all. Acha, what
Sir.
one question is there from Ravi Kumar sir that what actually the negative gain represents. So negative gain, the gain is nothing. It is depending upon how much power you are gaining in the input. If you will give 1 watt, that gain will become positive. But as we are limited with the power, and the area of the antenna that aperture is less, the gain anyway it is going to become as a negative because the size and the radiation performance due to the substrate anyway it is going to get reduced. But negative gain will have some value. It is not like the value will be negative. Means that it is in minus dB, right? dB in minus, but what you are giving, it will be very less. If you are giving 1 watt, it maybe you will be getting in microwatt. That is what negative gain means. Okay, so the power, what you are getting, it is not improved. That is what it is. Okay, one question is there, sir. Could you please suggest which simulation tool you use? ANSYS, what I have used was the ANSYS tool, ANSYS HFSS. Another question from Moko Pawan Kumar sir. It's how the thermal issue plays. Right, very nice question. And that is also another aspect. So thermal issue again, what we are working on the thermal part. Uh, we can use a heat sink also, but heat sink we are not. We will not suggest RFIC. Uh, Maybe some techniques, just like we are using for the crosstalk reduction, those techniques can be used for the thermal issue also. And that is also another area of research where we can work. Right. So very nice thermal issue also, just like in a design challenge also you can add. Is fabrication is necessary for general publication? Sir has asked. Okay, so sir, because antenna field is nowadays because every air antenna is fabricated. Without fabrication, what I have never nowadays there is no publication in antenna. In VLSI, where the devices people are working, they are just proposed maybe there it is possible to get a publication without. Fabrication also, and they are working without fabrication. But in antenna, I doubt it's very rare if we are able to get any publication. So that is what
So is
till
it,
now
it
I
is
have.
it is
One more
it,
question,
is it
sir.
must, sir? Is it must to for the fabrication? I mean, because the very limited facilities are available in India, as you said, I believe.
Right. Very limited. Uh, yes, sir. So that facility is very limited, but now when I have done 10 years ago, at that time very 2-3 labs was there. Still there is a if someone is not aware, I'll let me know tell. There is a Indian Nano User Program, which is run by the government. That IASC and all those people that Institute, IIT Bombay, IIC Bangalore, uh, these institutes have got those labs through that program only. So they are providing uh, free. Sometimes the first user, what if first they will review. If you send for the anything, any component for fabrication, they will review it. They will go through that. they will do some meeting with you, why you want to fabricate, what are the application. If they find good, in free also they will fabricate. For free also they will fabricate you. Otherwise, generally the charges after for the fabrication in India, it is 40,000, 50,000 for this on-chip antenna. Only fabrication. After that, they are asking for the that characterization also some 10,000 to 20,000. So that is a chance. But fabrication, without fabrication, and because the papers are coming from, the researches are coming from outside of the India, which are, they are having the facilities also for the fabrication. They are doing their fabrication, publishing the work. So if we are sending without fabrication, very hard to get it accepted.
Thank you very much, sir. Thank you, sir.
Thank you, sir. So I hope I have answered all the questions. If anyone has any other query, I have. I think I can. You can see
Sir,
my
how about the
email ID
opportunities
there
in
in the screen.
how about the opportunities in antennas compared to VLSI, sir? Because nowadays students focusing more on VLSI side.
That's right. So those who are really want to be in touch with the VLSI also, as well as they want to work in the antenna, this is the best field of the on-chip antenna. You will be working in the chip also, as well as you are working with the antennas. Means it is a bridge between VLSI and RF, you can say. So,
Sir,
you
one
can
thing
be
in continuation that question, I want to ask
yes,
you
yes,
one thing. That
yes, sir.
maybe we can start with the students. Maybe in simulation part,
Yes,
at
yes.
least simulation part is okay for their BTech projects. So,
Correct,
what do you
correct.
say, sir?
We
What do you
have
say?
also published some work in, yes, sir. We have
Hmm.
also published some work in the simulation also. Maybe, but mostly, again, that is some work is review and only conference. If we can limit ourselves till the conference only, because generally they are expecting a fabricated prototype. Or one work what I have done, we have done the equivalent model analysis also, and then for that equivalent model, we have done the IDS part also. So that comprehensive uh, research also without fabrication, one work I have published. So in that aspect also we can go for publishing in a journal. Then you need the complete
Okay,
focus
sir.
on
Thank
the
you, sir. Yes, sir. Thank you, sir.
that RF. Yes, sir.
Yes, sir. Anil, you can give what
Yes,
sir.
sir. Yes, sir. Yes, sir. Yeah. It's thank you very much, sir, for your present
Thank you,
session.
sir. Thank you.
It's my privilege to thank once again. I would like to extend my deepest gratitude. Whenever I asked about your session, you immediately accepted our invitation with no time. So we truly
It
appreciate
was
the
my
depth of your knowledge.
privilege, sir.
Yes, yes, yes.
Yes,
Long
sir.
back we tried to schedule, but due to other activities we couldn't. Now today it
Yes.
became true. So truly appreciating the depth of your knowledge and engaging the way you presented the blended topic of VLSI as well as the RF electromagnetics antennas. It's a very emerging field in the domain. This is very complex topic, sir. Participants we hope they got good takeaways from the session, and I must also express our heartfelt thanks to our chair, Dr. Naresh sir, and IEEE Vizag Bay section chair, Yasagan sir, and Secretary Sivakumar sir. Thank you, one and all.